I'm going to talk about the work that we're doing at Marine Smart Group at AUSTAL to how we're using the data that we're collecting across a lot of vessels to build predictive models and then use those models to optimize the vessel performance. And the talk today is pretty much concentrated and focused on the fuel consumption. And and also my colleague Max Van Sameren is also in the group, so we can actually together answer if there's any questions. Just to give you an idea about the objectives that we try to achieve in our work here. So basically, we wanted to be able to build really accurate fuel consumption prediction models that can actually predict the fuel under any loading or metocean conditions. So we also wanted to be able to do the similar thing to predict for motions of the vessels, take into account the environmental conditions, the vessel settings, the rod control system settings. We wanted to be able to do optimizations of the fuel consumption. So essentially not only predicting the fuel consumption, but also using those things to be able to optimize the vessel, how they run the vessel, how the operators actually run the vessel. And the same thing again, how we can actually do sort of like adaptive control, how we can actually control the motions of the vessels and optimize for the passenger comfort. And we wanted to be able to provide live advice back into the crew about how to set the settings. The parts that are highlighted in the blue are the ones that I'm going to talk about in this presentation, and the one in the black is that it's not a part of the current presentation. Give you a bit of overview of what we managed to achieve, and that I'm going to talk about in this presentation is that we managed to achieve a very good accuracy in our fuel prediction. We managed to be able to do real-time prediction and optimizations. We managed to achieve by deploying our advisor system on a vessel, on a high-speed vessel, we managed to achieve up to 4.5% fuel consumption improvement, and we managed to also achieve about 20% improvement in the motion comfort. And also we are able to provide live advice to the crew on the distribution of the motion comfort and sickness across the passenger deck at any location on the passenger deck. And again, the part in the blue are the ones that I'm going to actually focus on this presentation. The vessel that we deployed the model on, and the vessel that I'm going to show you as an example for our work today is called Buchanan Express. So Buchanan Express is a 65-meter catamaran built by AUSTAL and is operated by Fred Olsen Express in Canary Islands. It has a length of about 65-meter, displacement of about 650 tons. Generally during the operation, there has a speed of 28 knots. It travels, I will show you in the next slide the map of it, but it travels between two small islands in Canary Islands, in Canary Islands. And essentially that journey takes about 8 nautical miles and is planned for 25 minutes. So here, what you see is basically the route that is taking between the Playa Blanca and Corralejo, which are two ports in Canary Islands. And on the right, you see the water depths, basically the water depths map of the area. And it shows that the vessel is traveling something between 30 to 50 meter range of water depths. We've been collecting data since August 2018 as a part of the Marine Smart project. We collected data for about 1,800 journeys. And in order to analyze and build the models, what we did, we basically segmented or decomposed each journey into 3-minute segments. And we use each of that 3 minutes as a sort of as a data points in a row of data points in our models. This was because we wanted to be able to understand the influence of the variations like headings, variations of speed, variations of water depths. And that's why we had to actually decompose the journeys into smaller segments. And we also had that segments had to be small enough to capture the variation, but it also had it shouldn't be, it shouldn't have been too small, because otherwise we couldn't have seen the effect, the influence of the variations. And for each of these segments, we also collected the metocean from an external source, which relied on basically global metocean models. And we worked with a company called Tartek on that. So the data that we've been gathering data of fuel flow meters. And so the vessel equipped with 4 engines, and for each of the engines we had fuel flow meters that were actually giving us supply and return lines of the fuel. We've been collecting RPM for each of the engines. We had ultrasounds in front and aft of the vessel, so it was giving us the distance to the water surface. We've been accessing the data for the GPS, location of data. We've been accessing the speed over ground. We've been accessing because this particular vessel is equipped with the ballast tanks, and we had the ballast tanks at the forward and aft of the vessels, and we've been reading those level of the water at the ballast tanks. The steering, basically the angle of the water jets. The interceptor positions in this, because we have interceptor center, but in this vessel we had an interceptor, and we are getting the interceptor position. Motion control surfaces and settings, and we also had the IMU on board that we're calculating the accelerations and rotational motions of the vessel. To show just a bit of idea, so basically this shows some of the samples, for example, one particular journey that we collected the data of it for. On the left, you see the fuel flow meters on each of the engines, then on top, and then on the top right, you see the RPM. Bottom, basically left, you see speed over ground, and then on the bottom right, you see the steering angles. So generally, I'm not a naval architect, I'm a mechanical engineer, but I learned from the naval architect that you calculate the fuel prediction using the physics-based approaches. You rely on tank test data for your resistance, and you have your resistance as a function of your speed and water depths and different displacements, and might be in particular a couple of different trims. And based on that, you know your resistance, and you can actually, you also have your propulsion system with the water jet, for example, your thrust curves on top of that, so you understand what is your thrust, and then you can use the cube law to calculate the RPM and look at the engine performance curves to find the SFC, specific fuel consumption, and then from that one you calculate your fuel consumption. And this is essentially the physics-based approach, because you're relying on purely physical relationship between the known physical relationship between the parameters to calculate your fuel consumption. Of course, the issue with this is that it really depends on how good you know your resistance and how much tank tests you have done. And also in reality, the conditions are different and the performance changes by time. And also, pretty much it doesn't take into account the other resistance, wave resistance, or basically wind resistance. And all of those parameters have been added as sort of experimental values to it. But generally, these are basically the problem, which is the shortage of the shortcoming of the method. On the completely different way, you can actually build the models from data. So essentially, we build models from the observations, approximate models by the observations that we're making. We don't need to know any physical relationship, but it requires to have sufficient variation across different features. By features, we mean that, for example, different trims, different displacements, different water depths, and so on. And the problem with these models is, again, the accuracy drops if we want to use them outside of the conditions that they have been built the model on, based on those conditions. So our view was that, okay, what we can do, we can actually combine these two approaches and come with a hybrid approach. Basically, we use the physics-driven approach and the completely data-driven approach and combine them together. In a nutshell, if you want to look at it, essentially, we've said that, okay, if we're building a relationship between the x vector and the y vector, so x being our feature and the y being the labels means here the fuel consumption, and x are all of our features. So what we essentially want to do, we want to add an extra feature to our model, which is basically the theoretical fuel consumption. So what we're calculating from our white box model or the physics-based model. There are different ways to build this type of hybrid models, but we basically decided to go with a sort of naive approach that you just add a new feature to your model and basically to data-driven model. And that new feature is your physics-based driven model. So what we do, we essentially get for any measured data, from the measured data, we pass that into our physics-driven model. It calculates the theoretical field consumption, and then we bring back that theoretical field consumption plus with measured data into our data-driven model, and we build a predictive model on top of that, and that gives us a predicted field consumption. The approaches that we're doing, so basically we, because data-driven models are really depending on the quality of the data, so we spend a lot of time doing the data cleaning, and essentially if we have a missing data, there are several approaches to deal with the missing data, but we decided to actually just remove the data to make sure that it doesn't add any uncertainty into our models. And so we do, after that, we do a z-score calculation in each of our columns, and if any data point which is actually about z-score higher than 3, which means that it has a distance of more than 3 standard deviations from the mean of the data distribution for that particular column, we remove that. And then after that, we also pass it through the isolation files, which basically it relies on random forest for doing the final anomaly detection and removals. Then we go to building the predictive models, and what we do, we decompose the models, the data into 80%, 20%, and we use 80% to build our predictive model, and then test it on the 20%. So that 20% are completely withhold from the training duration to make sure that the model is actually have not seen any of those data sets. And so for each of the data points, we first calculate the theoretical field consumption, and then we add that into our feature, and then we build the predictive model. For the predictive model, we tested so many different predictive models, and we finally came with using the XGBoost model, which is based on the gradient boosting, and we find that it gives us the most accurate results, plus in a most efficient time of building the predictive models. It is really important to do the hyperparameter optimizations, and we do a grid search across all the XGBoost hyperparameters to actually optimize those, tune those things to give us the best answers. And then finally, we tested on our withhold test sets. So what you see here is, of course, the first step to look at how well the models actually do on a training set. And we see that our model in a training set, okay, it has a standard deviation error of 0.5%. So we have a very high accuracy in our training set, but that's the training set. The important thing is to look at the test set. We see at the test set, we actually have a standard deviations of 1.5%. And this is a really good result to be able to actually predict field consumption with such a level of accuracy. And this is on a data set that hasn't been seen by the model during its training. Of course, the important thing is once we build the model, it's really important to look at what are the important features, how this model is actually learning the relationships, and what features has the most significant impact on the accuracy of the model. And this is done by what we call it F-score, which is basically shows how many times these decision trees use a particular feature to draw a critical decision. And when we're looking at that, this is really interesting to see that the highest score is the theoretical field rate. So it means that our hybrid model is really important, because by combining the theoretical field consumption with the white box field approach into the data-driven, we can actually achieve a very good accuracy in predicting the field. It is interesting to see that we have a very high score in terms of the water depths. And this is really interesting, because if you look at from the physical point of view, if you look at it, that your resistance is really influenced by the water depth. So we can actually see that the model has understand the importance of the water depths. We see the importance of the environmental conditions, and for example, the relative wind direction, the relative wave direction, the relative current directions. We look at the speed of the vessel. trim settings, displacement, RPM, static trim. And these are really important because later on you will see that these are the parameters that we try to optimize the vessel, the settings. And we try to minimize the fuel consumption by optimizing these parameters. So if those parameters doesn't have an effect, then we can actually not achieve anything in terms of the fuel consumption. And you also see the influence of the, for example, the wave height, which is HSC here, a significant wave height. So of course, it's really important. Okay, building the predictive model is one step. At the end of the day, what we want to do, we want to deploy that into the system, and we want to actually optimize the vessel setting to be able to minimize the fuel consumption. So what we do, we deploy these models into the vessels in a real life, and we perform real-time optimizations, predictions, and optimizations. So basically what we do is that when the vessel is actually loaded, then we measure the distance to the water, and basically the draft at the from the sensor, we measure the draft at the forward and aft of the vessel. From that one, in real time, we calculate the vessel displacement and trim. Then we also, the models get continuously fed by the level of the ballast in the ballast tanks. And from that one, we know how much ballast we have in the tanks. We, on board of the vessel, at the pier, we're actually making API call to external sources and be getting the metocean data. Then we feed everything into a genetic algorithm optimization loop that then we go and optimize the vessel trim and basically interceptor positions, which and also the displacement, all of them together, to minimize the fuel consumption, which is getting predicted for each of the chromosomes or individuals of the genetic algorithm in real time on the vessel by using the predictive model that we built. And so to give you an idea of, so for example, what is happening, this is a very simple animation. So if you look at it here, is that on the x-axis, we have the aft ballast in the percentages. On the y-axis, we have the forward ballast, and then we have the fuel optimization. So I hope that you see the video when I'm playing it. I hope that you're seeing, so I assume that you do.
Yes, yes,
so
we can.
Yeah, so basically what it shows how fast our genetic algorithm actually converges into the optimum solution in finding the optimum settings, and this is a combined forward and ballast tanks for objective of minimizing the fuel. So this is interesting because we deployed this on the vessel in real time, and this is a video that actually Max took when he was on board of the vessel, and I want to show it to you. So this tablet in front is where the system is actually running, and we're giving the advice in real time. So basically we're feeding all the data, and then you can see here that, for example, the static trim in that part, we have the advice has been calculated in the real time versus the actual one. We're looking at the dynamic trim, the advice, and the actual one. We see that the crew here have been following that. And then this is also the comfort screen that we're calculating in real time what is the passenger comfort and sickness level in here as a single number. So this has been the system that has been deployed, and it does the prediction and the optimization in real time and provide advice of what should be the optimum ballast tanks and what should be the optimum interceptor positions. So to give you, then we wanted to understand how well it's working and how in reality, how well it was actually working. So we looked at the conditions when the vessel they were running the vessels, and we looked at the time that they were basically the time as a control conditions at the time that no advice has been provided to the crew. And the time that we provided the advice for interceptor, the time that we provided the advice for the ballast tanks, and the time that we provided the advice for both of them. And we looked at, for example, the number of times just to give you an understanding of how often we were giving these type of advices. And then we looked at the average fuel consumption in each of these categories. So essentially we filtered by the HS to make sure that all of them are in similar environmental conditions. And then we looked at, we compared everything to the basically the time that there was no advice has been followed. And you see that by following the interceptor advice, we managed to actually optimize the fuel by around 2%. and when by doing the ballast advice, something around 4% and 4.5%, 5%, then both of them combined has been followed. So it is interesting because it shows that this advice and this optimization in real life resulted in reducing the fuel consumption by 4.5% or up to 4.5%. And so our next step, so basically some of the works that we're currently doing, we're deploying this on a much larger number of the ships. And so basically there are prepared that we gather the data on each of these ships, and then we build the models, and then we deploy these models on it. We included in our advice the RPM optimization as well, and basically we're looking into influence of the optimizing the RPM such that they arrive on time plus they minimize the fuel consumption. And the next is one of the things that we are actually looking into is to combining, because we also have the model that actually optimize for the comfort, and this is optimizing the ride control system settings for the comfort. We want to actually now bring these things together and try to do the multi-objective optimizations and try to actually optimize for both fuel and comfort. And as you see the image on the right, so basically try to have a sort of weighting, whether the crew want to optimize more for fuel or for comfort. And then we're also adding more smart features to our model and to prediction. I think that's it from me.